Learning time. Until now, we have been concerned with the cases where the input is fed once. Altogether, in some applications, the input is temporal, where we need to learn a temporal sequence. In others, the output may also change in time. Examples are as follows. Sequence recognition. This is the assignment of a given sequence to one of several classes. Speech recognition is one example where the input signal sequence is the spoken speech and the output is the code of the word spoken. That is, the input changes in time, but the output does not. Sequence reproduction. Here, after seeing part of a given sequence, the system should predict the rest. Time series prediction is one example where the input is given, but the output changes. Temporal association. This is the most general case, where a particular output sequence is given as output after a specific input sequence. The input-output sequences may be different. Here, both the input and the output change in time. Time delay neural networks. The easiest ways to recognize a temporal sequence is by converting it to a spatial sequence. Then any method discussed up to this point can be utilized for classification in a time delay neural network. Previous inputs are delayed in time so as to synchronize with the final input, and all are fed together as input to the system. See figure 11.20. Backpropagation can then be used to train the weights. To extract features local in time, one can have layers of structured connections and weight sharing to get translation invariance in time. The main restriction of this architecture is that the size of the time window we slide over the sequence should be fixed a priori. Figure 11.20, a time delay neural network. Inputs in a time window of length t are delayed in time until we can feed all t inputs as the input vector to the MLP. Recurrent networks. In a recurrent network, additional to the feed-forward connections, units have self-connections of connections to units in the previous layers. This recurrency acts as a short-term memory and lets the network remember what happened in the past. Most frequently, one uses a partially recurrent network where a limited number of recurrent connections are added to a multilayer perceptron. See figure 11.21. This combines the advantage of the nonlinear approximation ability of a multilayer perceptron with the temporal representation ability of the recurrency, and such a network can be used to implement any of the three temporal association tasks. It is also possible to have hidden units in the recurrent backward connections, these being known as context units. No formal results are known to determine how to choose the best architecture given a particular application. If the sequence have a small maximum length, then unfolding in time can be used to convert an arbitrary recurrent network to an equivalent feedforward network. See figure 11.22. A separate unit and connection is created for copies at different times. The resulting network can be trained with backpropagation with the additional requirement that all copies of each connection should remain identical. The solution, as in weight sharing, is to sum up the different weight changes in time and change the weight by the average. This is called backpropagation through time. Ramon Hinton and Willis in 1986b. The problem with this approach is the memory requirement if the length of the sequence is large. Real-time recurrent learning is an algorithm for training recurrent networks without unfolding and has the advantage that it can use sequences of arbitrary length. Figure 11.21 examples of MLP with a partial recurrency. Recurrent connections are shown with the dashed lines. A self connections in the hidden layer, B self connections in the output layer, and C connections from the output to the hidden layer. Combinations of these are also possible. Notes. Research on artificial neural networks is as old as the digital computer. McCullough and Pease, 1943, proposed the first mathematical model for the artificial neuron. Rosenblatt, 1962, proposed the perceptron model and a learning algorithm in 1962. Minsky and Papert, 1969, showed the limitation of single-layer perceptrons, for example, the exclusive OR problem, and since there was no algorithm to train a multilayer perceptron with a hidden layer at that time, the work on artificial neural networks almost stopped except at a few places. The renaissance of neural networks came with the paper by Hupfield in 1982. This was followed by the two-volume Parallel Distribution Processing (PDP) book written by the PDP Research Group, which is Ramhart, McClelland, and the PDP Research Group, 1986. It seems as though backpropagation was invented independently in several places, at most at the same time, and the limitation of a single-layer perceptron no longer held. Figure 11.22, backpropagation through time A, recurrent network, and B is equivalent unfolded network that behaves identically in 4 steps. Starting in the mid-1980s, there has been a huge explosion of work on artificial neural network models from various disciplines: physics, statistics, psychology, cognitive science, neuroscience, and linguistics is not to mention computer science, electrical engineering, and adaptive control. Perhaps the most important contribution of research on artificial neural networks is this synergy that bridged the various disciplines, especially statistics and engineering. It is thanks to this that the field of machine learning is now well established. The field is much more mature now, aims are more modest and better defined. One of the criticisms of backpropagation was that it was not biologically plausible. Though the term neural network is still widely used, it is generally understood that neural network models, for example, multilayer perceptrons, are nonparametric estimators, and that the best way to analyze them is by using statistical methods. For example, a statistical method similar to the multilayer perceptron is a projection pursuit. Friedman and Stewart, though, 1981, which is written as y equals to summing th of w h to the transpose times x, where sigma is summing for all h starting from 1 to capital H. The difference being that each hidden unit has its own separate function, phi h dot. So in an MLP, all are fixed to be sigmoid. In chapter 12, we will see another neural network structure named radial basis functions, which uses the Gaussian function at the hidden units. I will skip it in our lecture. We'll go directly to chapter 13. There are various textbooks on artificial neural networks. Hertz, Grove, and Palmer, 1991. The earliest is still readable. Bishop, 1995, has a pattern recognition emphasis and discusses in detail various optimization algorithms that can be used for training, as well as the Bayesian approach, generalizing weight decay. Ripley, 1996, analyzes neural networks from a statistical perspective. Artificial neural networks, for example, multilayer perceptrons, have various successful applications. In addition to their various successful applications in adaptive control, speech recognition, and vision, two are noteworthy. Tesoros' TD Gallman program. Tesoro 1994 uses reinforcement learning, chapter 18, to train a multilayer perceptron and place backgammon at master level. Pomerleau's Alvin is a neural network that autonomously drives a van up to 20 miles per hour after learning by observing a driver for 5 minutes. Pomerleau, 1991.